准备开始。All right, we introduced Biot-Savant's law and we derived it. So now, once we know the current distribution, we can perform a closed loop integration to arrive directly at B vector. B is our magnetic flux density. So that is a very powerful tool. As compared to Ampere's circular law, we can now try to find out the result in B for arbitrary geometry. Okay, we don't rely on particular symmetries. So now let's take a look at one example. This is again a fictitious example. We have a wire of finite length of 2L. And we're now trying to look for the B field at an observation point which is bisecting the wire. So now we have one L and another L. So the observation point is here, bisecting the wire, and the distance is non-capitalized R. Right? We want to evoke Biot-Savant's law. So to use it, well, of course, we already know the current conducted by the wire, which is I. So all we have to know is when we perform the closed loop integration, we have to have a clearly defined differential length. And for each differential length, that piece of segment has a corresponding distance, capitalized R. And for each distance, we have to have a defined unit vector in terms of the distance vector. Okay? So all we have to do is find out the proper expression for differential length, the unit vector, and the distance for each piece of the current segment. So let's come back to the figure. Assume we're now trying to find the contribution of B field for this differential segment. So the differential segment has a length of dz prime. In this case, we want to use cylindrical coordinate. Why? Because a wire is best represented by cylindrical coordinate, right? Of course, the wire is not having its own radius, right? So the wire is positioned in the z direction, and therefore this differential segment is in the z direction, and each one is having a magnitude of dz prime. Again, I'm using the prime system to denote the source, right? Therefore, for this piece of differential segment, its distance to my observation point is labeled capitalized R distance vector. And that distance vector can be represented by the z location, the vector z, right? And the distance from my observation point to the bisecting point I denote as the origin of the cylindrical coordinate, right? So basically, this distance vector is the non-capitalized R vector minus the z vector, okay? So AR, R minus AZ, Z prime. Again, Z prime denotes the source coordinate. Well, this current form is having the non-capitalized R and Z prime, but eventually in this equation, I'm looking for something expressed in terms of the distance, the capitalized R, the magnitude of the distance vector. So somehow I want to express everything using capitalized R. So this R, now you draw this triangle from trigonometry. We know that the non-capitalized R is the capitalized R times sine theta. Theta is the angle here, okay? And Z prime is R cosine theta. So now we can express the unit vector easily by normalizing everything, just divide by R, right? This R vector divided by its own magnitude becomes the unit vector. So the unit vector is now in the R direction, the radial direction with a magnitude of sine theta, and minus the Z unit vector cosine theta, right? So now we know this. We know this. Do we know dl prime, the differential segment, differential length? Of course we do. It's in the Z direction and with a magnitude of dz prime, right? So now in the numerator, we can perform the cross, right? The cross product. So dl prime cross my unit distance vector. I can just write it out. Well, in this case, we're lucky. Why? Ideally, my unit vector has two components, right? Two directions. But eventually, my differential length is in the Z direction. So Z cross Z becomes 0, right? When you're making cross product, you have to have non-parallel components. So we're lucky we only have one resulting term. And this is a test to you. Z cross R. Z cross R, right? Z is now here, pointing upwards. Z cross R. R is here. Z cross R is, your thumb is pointing into the border, meaning the resulting direction is in the phi direction. So therefore, we have A phi, and the magnitude is sine theta dz prime. Okay? Therefore, the integration to use the Biot-Savart law, we only have to perform, well, in this case, we don't have a closed loop, but this equation works well, okay? We only have to limit the lower bound to negative L and upper bound to L to truthfully reveal the geometry, right? Totally, I mean, this segment has a length of 2L, right? But think about it. When we look at here, we are trying to integrate over Z, the locations of each differential segment. And if you look here, it's R squared is, well, seems like independent of Z. And sine theta, in this case, initially, naively, seems independent of Z prime. But that's not true, because whenever you change this theta value or this Z value, everything changes, right? If you try to integrate or try to find the contribution of this segment, theta changes, Z prime changes, the Z location changes, and R changes, right? So actually, these are all Z dependent. So we have to find a way to properly formulate everything in a single parameter, right? So the easiest one is to convert everything using trigonometry to be theta dependent. How can we do that? Well, look at the geometry. This distance magnitude is R cosecant theta, and Z prime is R cotangent theta. So now we find a way to convert the distance magnitude using theta, and also Z prime using theta. And from this equation, we can find the relation between dz prime and d theta. So we can convert everything using one symbol, theta. So theta is now becoming our variable. Okay. So after the conversion, I have a purely theta-dependent integrand. Okay. This is purely math. You have the notes, so you have to spend time on your own. I'm showing you the results, but there is one caveat. You have to be careful, right? The way I label theta 1 and theta 2 is extremely important. Why? To make everything consistent, when I'm trying to integrate the lower bound, I have defined theta 1 as the angle between z and my distance vector. Okay? Once I have defined theta in that way, when I change my theta value over to the top, when I reach positive L, the corresponding theta has to be defined in the same way. It's the angle of z and your distance vector. So this is actually my theta 2. It's not this one. Okay? You have to remain uniform. Your definition has to conform everywhere. So for the lower bound, the angle is z, between z and distance vector. So your upper bound has to be also the angle between z and the distance vector, right? So a lot of times students are making mistakes. Well, eventually the result is cosine theta 1 minus cosine theta 2. But if you define theta 2 incorrectly, then your results will be wrong. Okay? So what I'm trying to say is the value of cosine theta 2 is actually negative, even though this is cosine theta 2, right? You think, well, you have an angle, and if you take the cosine using this triangle, it's L divided by this piece. But to be correct, your cosine theta 2 has to be a negative value. If you take it positive, cosine theta 1 minus cosine theta 2, if you take it positive, you have 0. So why is cosine theta 2 negative? Well, if you still remember, cosine, positive, negative, negative, positive. Cosine is positive in the first and fourth quadrants, and negative in the second and third quadrants. Look at the geometry here. When I define theta 2 as this angle between z and r vectors, this angle is evidently greater than 90 degrees, right? Meaning theta 2 is actually pushing into the second quadrant. So if you're into the second quadrant, you have to know cosine must be negative, right? So you have a negative value. Well, another way to think about it is cosine theta 2 is negative cosine theta 2 prime, right? This theta 2 prime is positive, but because they are complementary, they add up to pi. So theta 2 must be a negative value. So this is a care that you have to pay attention to, right? In the end, if you do everything correctly, you will arrive at a beautiful result, right? For this wire with a finite length, the resulting B field is in the phi direction and with a magnitude of this expression. Now, if you still remember, we used Ampere's circuital law to find the B field of an infinitely long current conducting wire. Can you somehow just make some assumption so that the two results will merge together? How can we arrive at the result for an infinitely long wire? Well, you just assume L is going to infinity, right? When L is going to infinity, or L is much, much larger than non-capitalized R, this term is gone, right? And then you have mu 0I divided by 2 pi R. If you compare the result we got using Ampere's circuital law, they are identical. Okay? So every time, whenever you perform some calculation, at the end, don't just close the book or just turn in your homework or examination. Do some self-consistencies check, right? You have to, your answer needs to be tested, all right? So in this case, make L very big. You can ignore this one, therefore you arrive at your familiar answer for an infinitely long current conducting wire. Okay, next example. Well, if you still remember, Biot-Savart law has two formulations. One is using unit vector, another one is not. They are identical, but there are two different forms. So now I'm using another example. Okay, I have a closed loop conducting wire. So the circular loop is having current value of I, and the radius is B. Okay, it's B. Currently, I'm trying to find the resulting B field for an observation point of 0, 0, Z, which means I'm on the geometrical center, but now I have a height of Z. So again, this is only to illustrate the power of Biot-Savart law. But ideally, this observation point could be anywhere, okay, to make it more generalized. But at the moment, we are asked to find the B field at this particular point. Why? Because the textbook is trying to be nice. Think about it. When the observation point is on 0, 0, and having a Z value, it implies we have some beautiful symmetry. Okay? So at this moment, can you guess which direction is your resulting B field in? You are exactly at the center, the top of the center of this circular loop. Would you expect to have any radial component or phi component, or just simply Z component? Think about it. If you're trying to use Ampere's circuital law to solve this problem, then it relies on your deep understanding to the system. But if you use Biot-Savart's law, ideally, you just do everything, all the calculations brutally, and you will get the answer right. You don't really need to have physical insights or deep understandings. But that's not what I want to train you. I still want to train you in a way, before you perceive any problem, you can predict or foresee the result. Okay? So each piece of current segment is producing, well, your current direction in this case is going in the direction of the thumb. So your B field is following the direction of the four fingers, right? For example, this segment, right? So if I'm standing here, I should somehow feel the B only in the Z direction, because each segment would cancel out the other directions other than Z, okay? So if you have this anticipation in your derivations, even using Biot-Savart law, you would pay attention to some vanishing components, okay? All right, so in this case, for each differential segment, easy to describe, dl prime is b times d phi prime, right? Now we have a radius, so basically each differential segment is actually an arc. So b d phi prime defines the arc length, but in the direction of phi. My distance vector is this r, capitalized R vector, is therefore z vector minus my b vector, okay? Therefore, the magnitude, the distance of each differential segment to my observation point is therefore the square root of z squared plus b squared, okay? So I know this r. And I already know this dl prime, I know this r. I have everything. Right, so I can just do the cross product of dl prime to r vector. I write everything out. So this is the point where you have to decide again, if you understand the problem correctly and deeply, you can save half of the time as compared to your fellow students, fellow classmates. In the end, dl prime cross r vector is now arriving at two components, one in the z direction, another one in the r direction. Just like I said, do you want to put both components into the closed loop integration? Well, of course, if you don't have any physical insights, you don't understand this problem, go ahead and just do it. Put the two components into the closed loop integration. It's fine. If you do the math right, it's not affecting your result. But up front, if we only anticipate to have non-zero z component, which means the r component can be dropped at this moment. So think about it. As I mentioned, we don't expect to have any components other than z, which means at this point, this AR component must vanish. And therefore, you don't even need to bother to calculate it. But you have to convince yourselves. Why can't we just ignore that component? Well, it is because in the current case, we're trying to observe the B field at a beautiful phi symmetric point. We are exactly at the top of the center. So therefore, all the segments will give you R component and Z component, but eventually this one and that one will cancel out in terms of the R component. Okay? So in this case, it's due to the symmetry of my observation point being exactly at the top of the center of the circular loop. Therefore, you only have remaining Z component in terms of B. But if I change my problem to, well, my observation point is really arbitrary, you have to include this term into calculation. All right? Okay, so due to symmetry, we don't have any R component, we only have Z component, as we expected, right? Which is nice. So then you just perform the integration, and in this case, we're lucky because B is a constant, Z is nothing dependent on the source coordinate, so you just multiply by 2 pi. Okay? So this is the second example, but what I'm trying to tell you is, although Biot-Savart law is extremely powerful, but there are still moments that rely on your understanding prior to the mathematical procedures, and you can save time. Okay? In this case, you are dropping one contribution out, so in your integration, you only work for this one, you save 50% of the time. Okay? Now, having understood about how to use Biot-Savart law, I want to spend the next 25 minutes to talk about magnetic dipole. Well, if you still remember, I spent a lot of effort in multiple times, right, to explain and introduce and discuss electric dipoles. Now we're in the area of magnetism. Can we also formulate or just to define some equivalent thing as magnetic dipole as our basic field generating device? Okay? So once we define what is a magnetic dipole, we are going to find out the resulting magnetic potential and the flux density of a given magnetic dipole. And in the end, we want to compare the field structure between electric and magnetic dipoles, right? So I'm not going to spend any more time. I'm just going to tell you this is exactly the example which is finished. A magnetic dipole is nothing more than a circular loop with current I. Okay? Exactly the same problem we just solved. If we have a circular loop with a constant current, this loop has an area of S, right? So this area S and I somehow should give you a well-defined magnetic dipole moment. So we define the magnetic dipole moment. It is a vector, okay? It is a vector. The direction is the direction of the surface normal, right? The magnitude is the current multiplied by the surface area. Of course, you might be wondering, well, if I only have a surface, I might have two surface normals, one going up, one going down. So how to determine the right direction? Again, you use your right hand. Your forefingers should follow the direction of the current. Okay, so in this case, the current is flowing in a counterclockwise direction, and therefore my thumb points in the right direction to represent my magnetic dipole direction. Okay, so everything is still using the right hand rule. The forefingers denote the current direction, right? So in this case, since the current is flowing in a counterclockwise direction, making my magnetic dipole direction pointing upwards. Okay? Since, in this case, well, it's circular, so I know how to express my S, the The surface area is pi b squared. Okay. So magnetic dipole is also a vector. Its direction is determined by your current direction, and the quantity is defined by the current it conducts and the surface area. Now we have complete information. Okay? Let's try to find out the vector magnetic potential of a magnetic dipole. Again, what we're interested is when our observation point is very far away from this dipole. Okay? Which means this R or this R1 magnitude is very big as compared to the radius of the dipole. So this equation is now going to be used because this is something we work, right? The solution of three scalar Poisson's equations, and we combine them together. So once we know the current distribution, we can directly find the vector magnetic potential A. So all I have to do is, well, I have a well-defined differential length for each piece of segment on the dipole. And for each piece of segment, I need to correctly formulate its distance. Okay. So let's come back to this figure. Here, the textbook is trying to, well, first formulate or to find the potential at a particular point. This is in spherical coordinate. This capitalized R means the radius, theta is your inclination angle, and at this particular observation point, I am having a phi of pi over 2. So I'm exactly on the y-axis, 90 degrees y-axis. Okay? So this R is the distance from my observation point to the origin. But here, what I need is R1. R1 is the distance from my observation point to the differential segment I'm trying to investigate. Right? So somehow I have to formulate this R1 in terms of R, the distance to the origin, and the radius. But basically, R, R1, and B forms a triangle. So we know how to proceed. We have the adequate mathematical tool. First thing first, how do you properly express differential length vector? Well, its magnitude must be defined by B defined, right? Its magnitude must be defined as B defined prime because, again, you have an arc. And somehow, because in this coordinate system, even though we're using spherical coordinate system, but we have plotted the x, y, z coordinate. So the first thing is, again, before you proceed, we want to develop the capability to forecast, are there some components that would vanish, that will be canceled out, okay? So let us decompose A phi into x and y coordinate system. Ideally, dl prime is b defined in the A phi direction, which is correct, but that is not giving you physical insights. So let's decompose A phi into ax and y. So A phi is decomposed into the negative ax direction with a magnitude of sine phi prime, and the y component with a magnitude of cosine phi prime. Okay, So this is the moment where you have to think, well, do I want to put everything into my closed loop integration? Which means for each differential segment, it actually contributes to two components. One in the negative x direction. This is x, right? So negative x is actually into the paper. It also contributes a y component. Do I want to include both contributions into my integration? This is a point. This is a decisive point. Okay, let's try to plot out a circle. Okay, I'm trying to draw a circle, the cross section of my loop. If I'm trying to evaluate this piece of segment, then I can draw the dl prime, and then I can decompose it into the y component and x component. Okay. My observation point is somewhere here, right? Somewhere here. So symmetry tells me I can find another piece of segment here, right? Which is equally distanced to my observation point. What I'm saying is, since the observation point is to the right, so basically this segment and this segment would be somewhat equal. And this one will be somewhat equal. Okay? So for this piece of differential segment, I can find its counterpart here. They all have the same R1 value. Now, if I plot this dl prime, then something you notice. This is exactly how I decomposed each dl prime in the phi direction, but as phi changes, x and y component also follows the change of phi prime. But if you analyze only the green part, is adding up. But the yellow, for this one, the yellow part is pointing to the right, but for the top is pointing to the left. So they actually cancel out. Okay? So this is y, this is x. Okay? In the current geometry, x and y is defined in this way. So basically, only the green part is adding up. You don't have to calculate this contribution. It saves you time. Okay. So we plot that remaining contribution into calculation. Okay. Now be careful. We want to perform a closed loop integration. So therefore, I have to start from this point where phi prime is 0 and going all the way to 2 pi. Right? Ideally, phi prime from 0 to 2 pi means a closed loop. But as I stated, due to symmetry, this part is probably identical to this part, and this part is also identical to this part because eventually some terms would vanish. Okay? So in this case, I don't really have to integrate from 0 to 2 pi. I can only integrate from negative 2 pi over 2 to pi over 2. Means I only need to integrate from this part, this point, to this point, and multiply everything by 2. Okay? So I multiply by 2, so now in the denominator I have 2 pi. Initially I have 4 pi. By multiplying by 2, my integrants, the lower part, is now negative pi over 2. The upper part is pi over 2. So eventually I only have to integrate over a phi of pi instead of 2 pi. Okay? So this is my prior knowledge to this problem. They are somehow symmetric. Okay? Another piece of stuff I changed is negative ax direction is now converted into a phi direction. Why? Because my observation point is at a phi value of pi divided by 2. So at this case, at this particular position, a phi is exactly negative ax direction. Well, remember, I'm working everything in spherical coordinate, so I will only expect to see r, beta, and phi. I don't really expect to have ax. That's Cartesian coordinate. So in this particular case, negative ax for this observation point is a phi. Okay, so I have a phi. So now the problem is, well, we took care of the numerator. What about the denominator? Well, R1 needs some time, okay? But as I said, R1, and B forms a triangle. And if we assume this three-dimensional angle between R and B is called psi, capitalized psi, now using the law of cosine, we know that R1 squared is R squared plus B squared minus the multiplication of R and B, and multiply the cosine sine. Of course, you have a factor of 2. This is something we learned from high school, right? Cosine rule. And now we can use this fact to find the proper expression for R1. So this is purely math. All we're trying to find is, well, RB cosine phi, cosine psi. R and B is now having a three-dimensional angle. But if you remember, what is RB cosine psi? Whenever you have RB cosine, 2 magnitudes multiplied by cosine, which means you are actually performing the dot product of 2 vectors. Okay? You are trying to perform this R vector, making a dot product to this B vector. Even though the psi is difficult to find, but the end result will be identical if you take the projection of R onto xy plane, and then you make the dot product. Why? Because B is completely on the xy plane. So in making a dot product, the z component contained in R is not contributing. Right? So it would be identical to say this term RB cosine phi is equivalent to this vector, making dot product with this vector. We project this R onto xy plane. How to do that? Multiply by sine theta. Okay? So that's what we have. So we have some way to describe R1. But currently it's in R1 squared, but that's fine. Okay? We can just convert, right? We can just take the square root and invert it. Eventually, what we're interested in is 1 over R1. So this is 1 over R1. And if you still remember, I have made an assumption. My observation point is very far away from the magnetic dipole. So basically, this R is much, much greater than B. Okay? So I can drop this term out. I can make further assumptions using binomial approximation. So let me just show you the end result. Okay? A lot of things can be dropped out, but eventually, once you have a magnetic dipole, a current conducting circular loop, your vector potential would point in the phi direction, and with the magnitude of mu0, the vacuum permeability, multiplied by your magnetic moment and divided by 4 pi r squared. So another way to write it is, well, to truthfully reveal the magnitude and direction, the quantity is equal to your magnetic dipole moment making a cross product with the AR vector and divided by 4 pi r squared. This form might seem unfamiliar to you right now, but later I'm going to show you a direct one-to-one comparison of the magnetic part to the electrical dipoles, right? But now, if we have A, we can find B, right? All we have to do is perform the curl operation. Of course, we don't like curl, and especially now we're working in spherical coordinate. If you still remember the proper formulation for curl in spherical coordinate system, it's shown here. Okay, no worries. And we're lucky because we only have the A phi component. We don't have A theta component. We don't have AR component. We only have one single component. Okay? Very complicated calculation, but if you still remember this result, this is quite familiar to you. If you still remember electric dipoles, well, your examination is coming next Monday. Sin AR direction 2 cosine theta, A theta direction sine theta. This should ring some bell. I mean, you should still remember this. Okay? So in the end, I'm trying to show you a direct side-by-side comparison. This is the magnetic vector potential, A. If you compare to the electric potential, V, they are very similar, right? For electric dipoles, here I have 4 pi r squared. For A vector, I also have 4 pi r squared. The only difference is now I have 1 over epsilon 0, and now I have mu 0. Okay? So the end story is, if you master, if you understand one particular area very well, all you have to do is replace P by N, 1 over epsilon 0 by mu 0, and dot to cross. Look at it. P, if I change this one to N, right, I make the dot product to cross 1 over epsilon 0 to mu 0. They are identical. So these are the potentials. The magnetic potential, electric potential, you have to do this conversion. But if you look at the B field and E fields, again, you replace P by N, 1 over epsilon by mu 0. Everything is identical. So what does that mean? It means, well, in the far field, remember, all of our derivations for electrical dipole and magnetic dipole are assuming we are very far distance from the dipoles. And that's the definition of far field. We're very far away. So if I don't really tell you which dipole you're looking at from the far field, looking far away, I mean, can you tell which is which? They are identical. the field lines of an electric dipole and a magnetic dipole are identical. They're indistinguishable. You can only know which one is which by going into the near field when you walk very close to the dipole. So your distance is very close, which means you move this to gray areas. If you move into the near field, you would see, wow, they are so different. This one is having self-closed loop of field lines, but this one is having connected radiant field lines. So unless you go into the near field and where you can look and examine them closely, otherwise at the far field, in the far field, you don't feel any difference. Okay? So this one, tell yourselves, this one is the resulting field pattern for an electric dipole, right? Positive charge, negative charge, so therefore your field starts from the positive charge and ends at the negative charge. So the fields are actually radiant. But for here, you have the current loop. I'm looking at the cross section. So all the resulting magnetic field lines form closed loops around the current. Okay? So indeed, even though their construction might be very different, the near field patterns are very distinct, but in the far field, you cannot distinguish one from the other. Right? So for that, I'm going to conclude the first part of magnetic field. Next Monday, you're going to enjoy your examination. So next Wednesday, we're moving to magnetic fields with materials. Are there questions from the students? All right, so good luck next Monday.